Hey babe, could you guys just start real quick? Alrighty. Oh. There we go. Hello. Oops. Welcome to Monday. I think about that's all I have to say about today. It was a long weekend. I was grinding out the exam. I'll be dropping a post with more detailed information a little bit later. It's more or less the same as I already dropped a post about it, saying kind of general guidelines. I'll do a more intricate one, but it's more or less the same as previously advertised chapters. Oh man, they were the coolest thing I'd ever seen or heard back in my day, which I can refer to in the past tense, considering that I'm a father now. Okay, so today we'll see where it goes. The goal is to wrap up chapter 9. We have 2 weeks left, and I don't know about you, but I am at the point in the session where I am just tired, and I'm sure you are as well. We have 2 more weeks to push through, and then you all are free from chemistry. So anyways, let's go ahead and dive in. We wrapped up our discussion on Thursday of redox reactions, and we'll be finishing, hopefully, or coming close to finishing chapter 9 today, and it begins with a discussion of collision theory. All right, collision theory is a very important kind of a concept entity in the field of chemistry, and it has a very simple premise, and excuse me, kind of the basis of collision theory is the following. It's this: reactions occur when reactants collide. Kate, that is a great question. But since we're kind of moving on in lecture from redox reactions, let's hit that up in office hours tomorrow. Just because we're on a different kind of topic today, but office hours would be the perfect time to go over kind of some strategies on how to look at polyatomic ions. The quick answer, I can give a quick answer to that question, is you can take the polyatomic ion by itself and apply the rules for assigning oxidation states. The total charge will be whatever the charge of that ion is. But I can do some concrete examples tomorrow in office hours. Okay, so collision theory is the heart of collision theory is reactions occur when reactants collide. It's not a very complicated idea, but really where this starts hitting home is when you start thinking about what has to occur for a collision to take place, and this is what really leads us into kind of the heart of collision theory. To collide, reactants need to overcome the repulsion of their valence electrons. All right. So reactions occur when reactants collide. Of course, Kate. Anytime. In office hours, I guess. we'll get into it tomorrow. So they have to overcome. They've got to collide, and to do so, they've got to overcome the repulsion of their valence electrons. What are we talking about? Well, think about. I want you to consider this reaction, the reaction between calcium metal. So solid calcium metal, and chlorine. Sorry, that should be Cl2. These two react to make calcium chloride, which is a solid. Right, and to do this is a combination reaction, right? We got two things reacting, combining into one big thing, right? They form kind of like Voltron. And for this to happen, you've got a calcium atom, which we know has two valence electrons, and we have a molecule of chlorine, whose Lewis structure looks like this. And in order for this compound to form, these two have to react. They have to get close enough to each other to collide. You may be asking, what's stopping them? Oh, wow. That is not how you spell collision. All right, what's stopping them? And the answer is right here. You've got all of these valence electrons repelling each other. Okay, hang on. Yo, whoever's rhythmically banging. Oh, okay, no worries. Sorry. I apologize for that rhythmic banging. It actually wasn't my kids. It was one of my neighbors, so I guess we'll have to live with it. Okay. So their valence electrons repel each other, right? They all have negative charges, like charges repel. So in order for these two reactants to collide and react and form our molecule of calcium chloride, what has to happen is they have to have enough energy to overcome that repulsion, to get close enough to collide so they can exchange electrons and become the product that they're meant to be. All right? And when we talk about valence electrons repelling each other, the term for this is called activation energy. All right. Every reaction has an activation energy because every reactant has electrons. And so in order for those two to react, they've got to get close enough and overcome that repulsion, that activation energy, in order for a reaction to occur. All right. And the way we kind of depict the activation energy and what we call the energetics of a reaction are through something called a reaction coordinate diagram. All right, a reaction coordinate diagram. Now, here is, actually, I want to do that in yellow. Now, with a reaction coordinate diagram, it's a graph with a x and y axis. And on the y-axis, there's energy. And the x-axis is something called a reaction coordinate. And essentially, the way you can think about a reaction coordinate is its time, more or less. All right? And on a reaction coordinate diagram, near the origin, you have the reactants. All right? And then as you move away from the origin, you have the products. All right? And they're each at a particular energy level. And the reaction coordinate looks like so. You start at your reactants. Oh, it's a little ugly and wobbly. There we go. That's better. Oh, it dips down. Nope. Okay. Nope, I'm not gonna live with that. I can do better. There we go. I'm gonna live with that one. Okay, so this is right here what's known as the reaction pathway. All right, this is the reaction pathway here in blue. And it shows how the energy changes as your reactants become the products, all right? And the very tip right here, this tip of this peak, this is where the collision occurs. All right, that is where the collision occurs. This is this is called the transition state. All right, it's smack dab in the middle of reactants becoming products. Bolts. Sorry, that's my bad. Here, let me write just a little key. Yes, totally. Reacts equals reactants, and P. It's a D T S is products. Okay, so right at the tip of that peak, that is where the collision occurs. And you can see that there's an increase in energy as you move from your reactants towards that collision. Your energy increases, and that is the local maximum, right? Where the atoms are actually touching in physical contact with each other. That is the highest energy point. And then they move downhill as they move out of the transition state and become the products, all right? Now, the activation energy is right here. The distance between the energy level of the reactants and the energy level of the transition state where the collision occurs, this is the activation energy for your reaction, all right? So EA is a video game studio. It's also the energy of activation. All right, so there is the energy of activation. It is the difference in energy between the reactants and the transition state. All right, there's a second thing that we can get out of this graph, and that is the difference between, I'm actually gonna make it a different color. If you take the difference between the energy of the reactants and the energy of the products, this right here is the energy of the reaction, and you can see, because the products are lower energy than the reactants for this reaction, we would say that energy is released. All right. Energy is released in this reaction. And when energy is released, we say that the reaction is exothermic. All right. So this is kind of our introduction to a reaction coordinate diagram. We can see that it gives us information about how high the energy barrier is, how strong the electron-electron repulsion is between reactants and products. You can see that energy is released by this particular reaction because your products are lower in energy than your reactants. We therefore say that the reaction is exothermic. And there's one last thing that I want to stress here. When a reaction is exothermic, energy is released, you can consider energy as a product of this reaction. All right. So for exothermic reactions, you have your reactants becoming products, but one of the products of our reaction is heat. Heat is released. So an example of an exothermic reaction would be combustion. You light something on fire and it's hot. You're releasing energy into your surroundings. So it's exothermic. And that heat you can be is even though it's released, you can consider it as a product that the reaction is producing heat as it releases it into its environment. All right. Now, this is not the only type. There's two types of reactions. Basically, there's the one where the products are lower in energy than the reactants, and we saw an example of that just now. But the other type of reaction is a reaction where the reactants are lower in energy than the products, when the products are actually higher in energy. All right, and for this scenario, so we can draw our reaction coordinate. Again, this highest peak is where the collision occurs. This is our transition state. All right, and we can label our energy of activation because the energy of activation is the difference in energy between the reactants and the products. Between the reactants and the transition state. That is the energy of activation. And then the energy released by this reaction, or absorbed, as is this case, the change in energy for this reaction is the energy gap between the reactants and the products. And you can see here that the products are higher in energy than the reactants. So for this process, energy is absorbed. All right? Energy is absorbed by this process. And when energy is absorbed, we say that the reaction is endothermic. All right, the reaction is endothermic. And when you have a reaction that's endothermic, here energy is considered to be a reactant. All right. You can consider energy as a reactant. All right, so for endothermic processes, you have your reactants becoming products. And you can write in heat or energy on the reactant side of the equation because it's absorbed as you move from your reactants to your products. All right, so that is an endothermic process. All right, energy is absorbed or consumed. Now, there's a couple things that I want to kind of zero in and think about for a little bit. And the first is this concept of reaction rates. All right. Reaction rates. Oops. Yeah, the rate of a reaction is how fast a reaction occurs. And there are several factors that influence the reaction rate, how fast a reaction will occur, will take place. And the first factor that I want to focus on is energy of activation. All right, energy of activation. The energy of activation is the biggest factor that determines how fast, a reaction occurs, or I should say, not how fast, it determines the rate of the reaction. All right, and the large energies of activation equals slow reactions, and small energies of activation equal fast reactions. All right, so that is how energy of activation influences reaction rates. All right, that is the biggest factor. So if you were given two reaction coordinate diagrams, and you were asked which is fastest or faster, all right, and you looked at them, they both have reactants and products that are around the same energy level. One of them looked like this, the other looked like this. If you're asked to determine which is faster, you have to compare the activation energy. So there's the activation for one, here's the activation energy for the other. The larger the activation energy, the slower the reaction. So we would say that our second one is faster because it has a smaller energy of activation. All right. How large that activation energy will determine whether it's slow or fast. And this should be somewhat intuitive, right? You can think of the activation energy as a barrier of energy, right? Which mountain will it take more effort to climb, a small hill or Mount Everest? It's going to take a lot more energy to get up Mount Everest than it will to climb a little, knoll. Can I give real life examples of each rates? Yeah, totally. So like, for example, the activation energy for lighting some wood on fire is relatively low, or lighting the even better, lighting your gas stove. You turn on that striker, it strikes, and that's enough energy for the gas coming out to burst into flame. Relatively low activation energy, and the reaction occurs very quickly, right? It's just burning up. A large activation energy would be the decomposition of hydrogen peroxide, which slowly over time will decompose into H2O and, I almost said H2O and water, H2O and O2. Hydrogen peroxide decomposes, but it does this at a very slow rate because the energy to activation for that reaction is very high. So because it has a large energy of activation, it doesn't happen very quickly. It takes a long time. Because the combustion of methane has a low energy of activation, that reaction occurs very, very quickly. And actually, the funny thing about that one is the energy barrier is so low that the heat released by the first reaction is enough to activate the rest of it, to light the rest of the gas on fire. That's why if there's a gas leak and you light a match, you're going to run into an explosion. Excuse me. So that is this. So when we talk about the rate of reactions, how fast they occur, activation energy is like the primal thing, right? It's the biggest determining factor, but it's not the only determining factor when it comes to reaction rates. You can, when you think about increasing rates, a reaction's rate, its speed, will increase under conditions that increase the number of collisions that are occurring. All right. They'll increase with the number of collisions that are occurring. Now, so let's think about what could increase the number of collisions that occur. One big one would be concentration. I should say concentration of reactants. All right, that is one large factor that can increase the number of collisions that are occurring. Higher concentrations mean there's more particles, right? There's more reactants present, and so it increases your chances of the reactants colliding. So higher concentration will increase a reaction's rate. All right, that's one factor. Another one is temperature. All right, temperature can affect a reaction's rate. Now, here's the thing. The way temperature works, concentration works the same. Increase your concentrations, you increase your collisions. Temperature, I'm going to actually offset it in a different color because it's different. It varies depending upon exo or endothermic. For endothermic reactions, high temperatures increase reaction rates. All right, so that's true for endothermic reactions. For exothermic reactions, the opposite is true. Low temperature low temperatures increase reaction rates. And we'll talk about why for that second one. The first one makes sense. The second one, we'll talk about why that is once we get to chemical equilibrium. All right, the last thing that affects reaction rates is catalysts. All right, now a catalyst is a unique type of reactant. So a catalyst is a species that is not consumed over the course of a reaction, all right, catalyst is a species that is not consumed over the course of a reaction, and catalysts increase reaction rates by lowering the activation energy. All right, they increase reaction rates by lowering the activation energy. So, for example, let's look at a reaction coordinate diagram. Let's say we've got a reaction that looks like this. All right, so blue is a reaction. All right, and then in green here is going to be the catalyzed reaction. Now, it's the same reaction in the sense that we start with the same reactant and we make the same product. All right, but you'll notice that the energy of activation is much smaller for the catalyzed reaction than it is for the uncatalyzed reaction. So catalyzed reactions are faster because they have a smaller activation energy, but they start at the same reactant, produce the same product. Oh, Peyton. Peyton, that is a great question. That is an excellent question. And the answer to that question, so Peyton's question is, does volume affect reaction rates? And the answer is it can. It definitely can if we're talking about reactants that are in the gas phase or the aqueous phase. And the reason why and we've actually, believe it or not, low-key already talked about it, because concentration depends on volume. Right, so the most common concentration unit is molarity, right? And molarity is moles per volume in liters. So you'll notice that volume is in the denominator of molarity. And so they're inversely proportional. When volume is huge, your concentration is going to be small, right? And a low concentration means a slow reaction rate. When your volume is small, your molarity, your concentration is going to be large, and a large concentration means a faster reaction rate. So volume does affect the reaction rate because concentration is volume dependent. The two are inversely proportional. So if you want something to happen slowly, put it in a huge volume. If you want something to happen fast, don't give it a lot of room to roam. Put it in a small little volume so they're going to be banging into each other and the reaction will occur quickly. I should say quicker because there are more collisions. All right. Excellent observation. Okay, so that is our introduction to reaction rates. Yeah, totally. You are welcome anytime. This topic of reaction rates will flows seamlessly into our next topic, which is something called chemical equilibrium. Let's see, equilibrium. All right. So, to begin our discussion of chemical equilibrium, I want you to consider two chemical reactions. All right, consider the combination reaction that occurs when H2 reacts with I2 to produce two molecules of hydroiodic acid, all right, HI. All right, so this is a combination reaction. Combination reaction. Now consider the decomposition reaction. A reaction in which two molecules of HI collide with each other to form one molecule of H2 and one molecule of I2. This is a decomposition. All right, a decomposition reaction. Now, you'll notice something. You'll notice that the product of our combination reaction is the reactant of our decomposition. And the product of our decomposition, the products, are the reactants of our combination. All right, what's going on here? What reaction actually occurs, right? Does H2 and I2 react to make HI, or do two molecules of HI collide and form a molecule of H2 and I2? And the answer to that question is they both occur. This is an example of what is known as a reversible reaction. This is a reversible reaction. In a reversible reaction, the reactants of one are the products of the other, and the products of one are the reactants of the other. They swap roles, all right? We can write a reversible reaction like so. There's one reaction where it's H2 and I2 reacting to make 2HI, and then there is another reaction where two molecules of HI react to make H2 and I2. H2 and I2 reacting, this is called the forward reaction. And HI reacting with HI to make H2 and I2, this is known as the reverse reaction. All right, so you've got the forward reaction and the reverse reaction. Now, and they both are occurring simultaneously at the same time. Now, let's think about this for a little more. All right, so let's consider, I'm going to make a graph of the I'm going to make a graph where I plot the reaction rates, all right, of each of the forward and reverse reaction here. All right, so I'm going to put the rate on the y-axis, and I'm going to put time as the coordinate on the x-axis. All right, and with the forward rate, I'm going to plot in the salmon color, and the reverse rate, I'm going to plot in blue. All right. Now, at the very beginning of the reaction, all right, at the very, very start of things, hang on. Oh, there it is. Oh, hang on. There we go. Okay, so at the start of this reaction, again, the reaction where H2 and I2 react to make HI. And that is the forward, and this is the reverse. At the very beginning, we have it, before we make any HI, its concentration is 0. So the rate of the reverse reaction at the very start is 0, whereas the reaction rate for forward reaction is high because the concentration of H2 and I2 are high. As this reaction starts, H2 and I2 start to be consumed, so their concentration drops and their reaction rate drops. In addition, the concentration of HI builds up as the reaction starts. So the rate of the reverse reaction has a little increase. As the reaction goes on, the rate of the forward reaction continues to fall because the concentrations of the reactants are decreasing as they react away, whereas the rate of the reverse reaction continues to rise because the concentration of HI is increasing. And eventually, they hit one magic point where the rate of the forward reaction and the rate of the reverse reaction are the same. And for every point from there on out, the rates will be equal. And this is because the concentrations have reached a point where as fast as the forward reaction is producing HI is reacting to reproduce H2 and I2. All right. So if you plot these two lines, they'll look like this. Oops. All right. And from this, oh, hang on, I can draw that better. All right. And from this moment on, the rates are the same. The rate of the forward and the rate of the reverse. All right. They're the same. And once they hit this spot, where the rate of the forward reaction where the forward rate is equal to the reverse rate, this is what we call chemical equilibrium. This is the definition of chemical equilibrium. All right, it's when the rate of the forward reaction is equal to the rate of the reverse reaction. All right? Chemical equilibrium. Now that we know what chemical equilibrium is, we can talk about what's known as the equilibrium constant. All right. The equilibrium constant is abbreviated with a capital K and a subscripted EQ. KEQ is the equilibrium constant. Every reaction has one. All right. And KEQ tells you the relative concentrations of products versus reactants when a reaction is at equilibrium. All right, it tells you the relative concentrations of products versus reactants when a reaction is at equilibrium. So taking a generic reaction where you have A reacting with B reversibly to produce C and D. And just to be clear here, these are all the stoichiometric coefficients. All right, those are the stoichiometric coefficients. Your equilibrium constant for this reaction is equal to it's always products over reactants. So it is the molarity of C raised to the power of C times the molarity of D raised to the power of D over the molarity of A raised to the power of A times the molarity of B raised to the power of B. Again, the stoichiometric coefficients in this reaction are all the superscripts. All right, and the thing to note is here in the numerator, you have products, and in the denominator, you have reactants. All right, so you've got products, you've got reactants, and then another new thing that we're introducing here is are these brackets. So whenever you see something thrown in a bracket, like if you saw, for example, this means the molarity of NaCl. Or that's what those brackets mean. So it's the molarity of product C raised to the power of C times the molarity of product D raised to the power of D over the molarity of A to the A times the molarity of B to the B. All right. So this is the equilibrium constant. One thing to note, and unfortunately I got to go to a new page here. So something that you should know and be careful of is solids and liquids have no concentration. This is because they are pure substances. Right? They're not mixtures. They're pure substances. So, as a result, only gases and aqueous reactants or products are included in the equilibrium constant. Now you may be going, well, wait a minute. Hold up, Josh. Gases can be pure substances. They can. But they still have concentration because they have varying volume. So take a look at PV equals nRT. Check out PV equals nRT. Watch what happens. I'm going to do some fancy footwork. Algebraically. I am going to multiply both sides by RTV. Multiply both sides by RTV. Well, volume cancels on this side. And on this side, RT cancels. What do we have left over? We have P over RT equals N over V. All right. Think for a minute about our units here. N has units of moles. Volume in the ideal gas law has to have units of liters. And moles over liters equals molarity. So, yes, gases are pure substances, but the ideal gas law shows us that the molarity of a gas is equal to pressure of the gas over R times T. So even though gases are pure substances, they still have a concentration, they still have molarity, and they're still included in the ideal gas law. All right? So we've done a lot of kind of talking, a lot of going over kind of in an abstract sense, what is chemical equilibrium, what is the equilibrium constant. Let's start doing a few concrete examples. All right, so let's write the expression for the equilibrium constant for the following reaction, or the reaction between NO decomposing into N2 gas and O2 gas. All right, well, the thing to remember about KEQ is it's always products over reactants. All right, that is always the ratio. It's always products over reactants. So the products for this reaction are nitrogen. We got to do the molarity of nitrogen. Now in this reaction, nitrogen has a stoichiometric coefficient of 1. So nitrogen is raised to the power of 1 in the equilibrium constant, and the same is true for oxygen. It has a stoichiometric coefficient of 1, so it's the molarity of O2 raised to the power of 1 over reactants. In this case, NO2 is the only reactant, but because it has a stoichiometric coefficient of 2, we square it. All right, so this is the expression for the equilibrium constant of this reaction. Let's do another example. How about the reaction between aqueous silver nitrate and aqueous calcium chloride which produces aqueous calcium nitrate and solid silver chloride. All right, again, remember, we're products over reactants. So KEQ will equal the concentration of calcium nitrate. That looks like a C. It should be a parentheses. And this has a stoichiometric coefficient of 1, so it's to the first power. All right, but check this out. Our other product, silver chloride, is in the solid phase, so it's not included in the equilibrium constant. Only phases with concentrations are included. So that's the only product that makes it into our equilibrium constant. On the reactant side, we have silver nitrate. Oh, whoops. Sorry, I wrote this wrong. This should just be AgNO3. There we go. And because this has a stoichiometric coefficient of 2, we square the concentration of silver nitrate, then multiply it by the concentration of calcium chloride. All right, so this is the equilibrium constant for this reaction. Solids aren't included, liquids aren't included, only aqueous compounds and gases. So this is the expression for KEQ. All right, let's do another example. This one is a little bit different. So this example says write a balanced chemical equation for a reaction containing all gas reactants and products whose equilibrium constant is this. Let's see. I'm going to scoot this down a little bit. So NO to the fourth times H2O to the sixth over O2 to the fifth times NH3 to the fourth. All right, now this may seem dizzying. It may seem like a doozy. You may be going, how could I possibly do it? But it's actually not that bad. Once you remember that the numerator up here, these are your products, and the denominator holds your reactants. So first step, our reactants are O2, gas, because we're told everything was a gas, plus NH3, also a gas. And our products are NO gas and water vapor. Now you may be going, yeah, but now we have to balance it. No, you don't actually. Because remember, your exponents here are all your stoichiometric coefficients. So that means we have 5 molecules of O2, 4 molecules of NH3, 4 molecules of NO, and 6 molecules of H2O. This is your final answer. It's actually not that bad moving from a equilibrium constant in reverse to the balanced chemical equation. Excuse me. Okay. I think this is where we're going to end things today. We're almost done. We just have just a little bit left in Chapter 9, so we'll polish off Chapter 9 tomorrow and dive into Chapter 10, which I've been looking forward to because then we get to get into acid-base chemistry. So we'll go ahead and pause things here, and I will catch you all tomorrow. Susan, great question. So this is actually a really good thing to keep in mind. Water can be a liquid or a gas. It doesn't have to be in the liquid phase. It can actually be a solid too, right? Liquid, gas, or solid. And in this specific problem, we're told that we have all gas reactants and products. So here, we actually don't have liquid water. We have water vapor, otherwise known as steam. So if water was in the liquid phase, it would not be included, which is Susan's sharp eye, and it is something to be looking for. But, yep, totally. Water can also be in the gas phase. So that's another reason why, actually, and I think this should be stressed. You always got to keep an eye out when you're doing the equilibrium constant problems on the phases, because you can't just look at water and go automatically yes or automatically no. It'll depend upon whether it's in the liquid phase or the gas phase. But the good news is you will always be explicitly told, all right? You'll never have to wonder, like on your own, is it liquid or is it a gas this time? I will always tell you what it is. It's just up to you to catch what it is and remember how to apply that. Cool? Alrighty. Awesome questions. It's weird. So we're done with lecture. This is the second to last Monday we have together the summer session. Next Monday's our last Monday. This is our second to last week. It's exciting and terrifying all at once. I will catch you guys all tomorrow, same time, same place. Later.